This is our paper, Foreground Focus, Enhancing Coherence and Fidelity in Camouflaged Image Generation. Our work is motivated by a recent method called Lake Red, which generates camouflaged image using only the foreground object and retrieves compatible background knowledge from a pre-trained codebook. These two sets of features are then used as conditions to guide the latent diffusion model to synthesize a camouflaged image. However, we observe two weaknesses in Lake Red. First, the generated background often lacks consistency with the foreground, such as mismatched texture, which weakens the camouflage effect. Second, the foreground tends to be heavily distorted, especially when the object is small, leading to unnatural appearance. These two issues significantly degrade the visual quality and realism of the generated camouflaged images. To address these two issues, we propose a method called FOSIG. First, we design a module called the Foreground Aware Feature Integration Module, or FFIM, to enhance the foreground-background consistency. Second, we revise the original denoising loss, used in the LDM, and propose a new foreground-aware denoising loss to better preserve the foreground fidelity during generation. This is the structure of our proposed model. It's built upon a latent diffusion model with a VQ via E backbone. The generation is conditioned on two components: the foreground features we want to preserve, and the background knowledge we retrieve based on the foreground. The background reconstruction pipeline involves three stages: compression, background knowledge retrieval, and foreground-aware feature integration. In the first stage, we extract the foreground features. Since camouflaged objects are usually small, directly resizing the entire image would lead to a significant loss of foreground information. To prevent this, before resizing, we crop the foreground first to retain the detail. Then, we mask out the background and extract the foreground features. In the second stage, we follow Lake Red to retrieve background knowledge based on the foreground features. We use the SLIC algorithm to divide the foreground into superpixels, and then average the features within each superpixel to obtain representative foreground features. These features are used as queries to retrieve semantically compatible background knowledge from a pre-trained code book. In the last stage, we proposed FFIM, an attention-based module, to enhance the interaction between the information from foreground and background. We combine mask embedding and position embedding to inform the model about different spatial regions. Through a series of attention layers, we allow the background regions to be aware of the foreground features, encouraging better visual consistency. Finally, we obtain the background feature representation, which is then used to guide the generation process. Now that we've integrated the foreground and background features, the next step is to ensure the foreground fidelity. As mentioned earlier, camouflaged objects are usually small, so the background tends to dominate the denoising loss during training. So we design a weighting factor to upweight the foreground regions. The weighting factor is defined as the inverse sum of alpha and r, where r is the object ratio, and alpha controls the upper bound. The smaller the object is, the more the loss focus on reconstructing the foreground. This slide shows visual comparisons between Lake Red and our method. On the left, you can see that our method generates camouflaged images with better texture blending and overall visual quality. We also use general objects to evaluate the model's capability for transferring non-camouflaged images to camouflaged. On the right, our method clearly preserves more fine-grained details, especially for small objects. This is the end of our work. Thanks for your attention.